to find the magnetic field at a certain distance away from a proton moving into the page with a speed of 0.01 c. Okay, so let's do the magnitude of the magnetic field first. So to find the magnitude, we use the Biot-Savart Law, which says that the magnetic field is equal to mu naught divided by 4 pi times q times the velocity crossed with r hat divided by r squared. So that gives us the whole vector. For the first part, let's find the magnitudes. The second part, we have to draw it, so we'll worry about the directions for that part. So what numbers do we know to put in here? Mu naught is our constant, the permeability of free space, 4 pi times 10 to the minus 7 Teslas times meters over amps. Q is the charge of a proton. That charge is plus E, 1.6 times 10 to the minus 19 coulombs. V is our speed. That's given as 0.1 c, so 0.01 times 3 times 10 to the 8 meters per second, which is 3 times 10 to the 6 meters per second for our V. And then our R is going to be our distances, each in turn 1, 2, and 3 micrometers. So for part A, B equals mu naught over 4 pi times our charge Q, 1.6 times 10 to the minus 19 coulombs. Okay, so the magnitude of our magnetic field is going to be mu naught over 4 pi times our charge Q. The magnitude of V cross R is just V, so times V, 3 times 10 to the 6 meters per second, divided by R squared. So for part A, that distance is 1 micrometer, 1.0 times 10 to the minus 6 meters, that's squared. Put that through the calculator and we should get a magnetic field of 4.8 times 10 to the minus 8 Teslas. So that equation we used for magnetic field came from our Biot-Savart. So the magnitude of B is magnitude of B equals mu naught over 4 pi times Q times V times sine theta over R squared. And in our equation, we're going to take it into the plane, so our theta is always 90 degrees. Okay, so we use this equation to find the magnitude of the magnetic field. That's at 1 micrometer. Part B has R equals 2 times 10 to the minus 6 meters. Okay, I won't write the equation out again, but the magnitude of the magnetic field in this case is 1.2 times 10 to the minus 8 Teslas. And part C, our distance is 3 micrometers, which gives a magnetic field of 0.53 times 10 to the 8, 10 to the minus 8 Teslas. So we see that the further away we get, the smaller our magnetic field get, which makes sense because it falls off as 1 over R squared. So these are our magnetic fields. For the direction, let's answer that as we draw the magnetic field vectors. So here's our proton. Let's think about our bottom one, our biggest distance out. Here's our proton that's moving into the page. Let's ask, what is the direction of the magnetic field vector right here? Our velocity is into the page. We'll draw an X with a V to show our velocity vector. R is the vector. So if this is our point P, R is the vector from our charge to our point. There's our vector R. And R hat is the unit vector, which points out in the same direction as R. So to do our right-hand rule, which applies to positive charges, velocity vector is our thumb, the R hat vector is our index finger, and the result, the magnetic field, is our middle finger. So let's see if we can work this out. Our velocity goes into the page, so our thumb points down into the page. Our finger goes with R, and our middle finger shows B, so it goes straight to the right. So at this point, the magnetic field points this way. Well, that's okay for right here, but that's not the only place where we have a distance of 1 micrometer. We also have a distance of 1 micrometer, say right here. And at this point, we'll switch to a different color. At this point, here's the r vector this time. So now that direction has changed. Now it points this way. So here's where we see that r and v are perpendicular. R points this way, v is into the page. There's 90 degrees between those guys. So v is into the page, r is this way, and then we see the direction of our magnetic field points this way. So tangent to the circle with the orientation given by that right-hand rule. So there's our b for this guy. And what if we wanted to do down here? Let's pick one more spot, and we'll see what's starting to come out. So here, we're still 3 micrometers away. This is our r vector from our charge to our point. This is our r hat, which is the same direction as r. And let's find the direction. V is into the page, finger goes with r, middle finger shows our b, which is tangent to the circle, comes around this way. What we see is that the magnetic field makes circles around our moving charge, and those circles have an orientation given by the right-hand rule, where our thumb is V, our index finger is R, and our middle finger is B. So at every point we have an arrow that points this way. The end result is that those magnetic fields are circular. So in every point, the magnetic field is perpendicular to R and perpendicular to V, so it makes a big circle going around the wire. So this is the magnetic field at 3 micrometers. The magnetic field at 2 micrometers is a little bit small, it's a little bit bigger, and it happens in closer. So we would do exactly the same thing to find the direction, and we would see that that also makes circles, where the orientation comes around the same way. And at 1 micrometer, it's still circles, so we're still coming around this way. So there's the magnetic field. So when we want to make these vectors, the direction, circles, and we use the right-hand rule to show the orientation of those circles. Okay? And at any one spot, it's a tangent to the circle.